You are watching AI paper slop. The entire machine learning industry might literally be wasting a massive amount of time in compute right now. There's this new paper out of Microsoft Research by Yuxin Zheng and Dimitris Papiliopoulos called "You Don't Need to Run Every Eval." And it just proved that the standard practice of running, 40 to 100 benchmarks for a new model release is mathematically redundant. So if you are an ML engineer managing an evaluation budget right now, here's your TLDR. The researchers basically compiled this massive public score matrix of 84 frontier models across 133 benchmarks. And they found that this entire capability matrix is effectively ranked 2, meaning a model's whole capability profile across coding, math, agentic tasks, and reasoning is largely determined by just 2 latent numbers. So to exploit this, they built a tool called BENCHPRESS. Instead of spending thousands of dollars and days of compute on the full evaluation suite, you run 5 specific benchmark probes, and BENCHPRESS recovers the model's full scorecard from that rank 2 geometry to within about 4 points of accuracy. Okay, let's unpack this.
Yeah, to really understand how massive a paradigm shift this is for, evaluation economics, we really have to look at the underlying data structure they use to prove this rank 2 theory in the first place.
Right, because garbage in, garbage out.
Exactly. We all know that in machine learning, the algorithm is only as good as the underlying data distribution. And building this specific data set was a phenomenal data engineering challenge because, frankly, benchmark reporting in our industry is completely fractured.
Oh, web scraping for ML evaluations is an absolute nightmare.
It really is.
I mean, there is no centralized, standardized repository where every model is tested under the exact same conditions. If you want a comprehensive matrix, you are dealing with different evaluation harnesses, custom vendor scripts, third-party reproductions.
And they rarely match the official technical reports.
Right. So how did they actually build this thing?
Well, they started with a seed queue of well-known frontier models. So, GPT 5.5, Claude Opus 4.7, Gemini 3.1 Pro, DeepSeek V4 Pro, and they built a recursive crawler.
Okay, that makes sense.
Yeah, so they scraped official release blogs, system cards, technical reports, Hugging Face model cards, and here's the clever part. Whenever a technical report mentioned a competitor baseline, they used that mention as a node to recursively discover and scrape even more models.
Oh, wow. So they turned the scattered bragging rights of the AI industry into an actual structured graph.
Precisely.
Yeah.
And they supplemented all this by sweeping major public leaderboards like Matharina, ARC Prize, and LiveBench just to fill in the missing edges.
But wait, throwing raw, scraped benchmark data into a matrix completion algorithm is usually a recipe for disaster.
Oh, absolutely.
Because of the variant problem, right? Vendors are constantly massaging their numbers. One technical report might showcase a 5-shot score with a complex chain of thought prompt, while a third-party leaderboard uses a 0-shot direct answer prompt for the exact same benchmark.
Yeah, and if you treat those as 2 distinct data points, you just artificially inflate your matrix density with redundant, highly correlated signals.
Exactly. So how do they trust this data?
They applied a strict canonicalization process. So for every model, they fix one canonical configuration, prioritizing the specific prompt and temperature setting the vendor itself foregrounded in its official communications.
Okay, that filters out a lot of the noise.
Right. And they did the exact same thing for the benchmarks, keeping one canonical column per task family to basically compress out those redundant scaling variants. Then they filtered out the long-tail models and obscure benchmarks that just lacked enough statistical support.
So they finally landed on this dense target matrix.
Yep, 84 frontier models by 133 benchmarks.
But even with that aggressive curation, we are looking at a matrix with, only 2,604 observed cells?
That's right.
So that is a sparsity level of about 76.7%. I mean, more than 3/4 of the scorecard is completely blank.
It sounds bad when you put it like that.
Well, it's like trying to reconstruct a high-res image from just 1/4 of the pixels. If this matrix is more than 75% empty, we are flying blind. The only way to predict the missing scores is if the data we do have follows a highly rigid, predictable geometry.
Which is exactly what they found.
The rank of the matrix. How did they actually prove this is a rank 2 manifold?
So they carved out the largest fully observed submatrices they could find within that sparse data set. And they ran singular value decomposition, or SVD.
Okay, standard linear algebra approach.
Exactly. When you apply SVD to these dense blocks, you are essentially looking for the principal components of the capability space. And they looked at the resulting singular values and found this massive spectral gap
Meaning what, exactly?
Meaning just two singular values, just two latent components, explain more than 90% of the total variance across all the models on the benchmarks they share.
Okay, I have to challenge the reductionism here.
I figured you might.
I mean, are we honestly saying that all these highly diverse, complex skills, writing a functional web app in Python, passing the uniform bar exam, doing nuanced creative writing, and solving AM competition math, all of that collapses into just two mathematical dimensions?
It does.
But how can the manifold of frontier AI capabilities be that flat? What happened to the idea of specialized models?
What's fascinating here is that this actually aligns beautifully with the psychometric concept of the G factor, but applied to artificial intelligence.
The general intelligence factor.
Right. Prior work, like studies by Burnell and the Epoch AI Capabilities Index, they've hinted at this low-rank structure for a while now. The dominant singular value, that first dimension, captures that general capability axis.
So if a model is just generally huge and well-trained, it's good at everything.
Basically, yeah. If an LLM has the underlying parameter count and training compute to master complex multi-step coding tasks, information theory dictates it will almost certainly have the latent representation power to crush complex science or reasoning benchmarks. The variance is just heavily correlated.
The rising tide lifts all boats.
Exactly. Overall model strength is the primary axis.
So if the first dimension is just raw power, what does the second dimension capture?
The second dimension roughly maps to a provider-specific residual.
Like an OpenAI flavor versus an Anthropic flavor.
Exactly that. It captures the slight stylistic or algorithmic biases injected by specific pre-training mixtures or alignment strategies. So, OpenAI's specific reinforcement learning from human feedback might penalize certain types of verbose answers, while Anthropic's constitutional AI constraints might shift performance slightly on subjective tasks.
Oh, I see. So that second dimension captures the alignment tax and the tokenization quirks.
Yep. And beyond those two vectors, the remaining variance in the matrix is essentially just statistical noise.
Wow. Okay, so if the underlying capability structure is that heavily constrained, it actually makes predicting the missing 76% of the matrix a completely solvable problem.
It does. But, going from a theoretical SVD observation on a dense submatrix to actually imputing thousands of missing values on a highly sparse matrix.
That requires a real algorithmic engine.
Right. And that's why they built BENCHPRESS. But they didn't just default to standard matrix factorization.
So what did they use?
They ran an exhaustive grid search, testing 12 different prediction methods, everything from k-nearest neighbors to Bayesian ridge regression, paired with 7 different feature transforms.
And the winner was?
The definitive winner was a rank 2 alternating least squares, or ALS, matrix completion method operating specifically in Logit space.
Oh, let's talk about that Logit space transformation, because that is a crucial engineering detail.
It really is.
Because ALS is a linear algorithm, but raw benchmark scores are strictly bounded percentages, right? Between 0 and 100.
Exactly.
And that creates massive saturation effects at the extremes. I mean, moving from a 98% to a 99% on a basic MMLU task requires vastly more underlying algorithmic capability than moving from a 50% to a 51%. It's a highly nonlinear capability curve.
You nailed it. By transforming those raw percentage scores into Logit space, they map the 0 to 1 bounded interval onto the entire real number line.
Stretching out the tails.
Exactly. It stretches out the sigmoid curves of capability at those extreme tails. And this allows the ALS algorithm to linearly model the latent capability vectors without artificially compressing the variance of frontier models that cluster near the ceiling on easy benchmarks or the floor on brutally hard ones.
And it mathematically prevents the algorithm from predicting impossible scores, like, 105%.
Right, which standard linear models will sometimes do if you don't transform the space.
So operating in Logit space allows ALS to factor the partially observed matrix by alternating between fixing the model vectors and optimizing the benchmark vectors, converging on that latent rank 2 structure.
And the results they got are honestly impressive. BENCHPRESS predicts the held-out model benchmark cells with a median absolute error of just 4.6 points at 100% matrix coverage.
That's incredibly tight. But what I really love about this paper is that they didn't just benchmark ALS against other statistical methods. They pitted BENCHPRESS against an actual frontier LLM acting as a judge.
Oh, the showdown with GPT 5.5. Yeah, this was Brilliant.
Wait, they seriously used a frontier model to guess its own benchmark?
They did. They designed a head-to-head showdown. They gave GPT 5.5 a prompt containing a few peer models and their scores, and basically asked it to infer the missing benchmark scores.
Okay, how did they structure it?
They ran this in two distinct settings. First, the informed setting, where GPT 5.5 was given the actual semantic names of the models and the benchmarks, so it knew it was looking at Claude or Llama.
Okay.
Then the blind setting, where all identifiers were completely anonymized, leaving only the raw numerical relationships, model A, benchmark B, that kind of thing.
I found the result of that blind setting so revealing because it's hilarious, right? When you strip away the semantic names, GPT 5.5's prediction accuracy just completely falls apart.
It does.
It proves that the LLM wasn't actually doing numerical inference or understanding the latent geometric structure of the matrix at all.
No, it was just overfitting to its own training data regarding model taxonomy.
Right. It relies on a memorized semantic prior, knowing that a Claude Opus model generally beats an older Llama model to just guess the score.
Exactly. When forced to rely purely on the math in the blind setting, the classic ALS algorithm utterly destroys the frontier LLM.
I love that. It's such a massive vindication for traditional statistical learning over just throwing an LLM at every problem.
Absolutely. And plus, from a systems engineering perspective, BenchPress is infinitely more scalable. I mean, you fit the matrix mathematically once in seconds, rather than querying a heavy, expensive LLM API thousands of times to run inferences on every single missing cell.
Totally. So let's get practical here. If I am an ML engineer, I do not want to run all 133 benchmarks during a hyperparameter sweep.
Nobody does.
Right. I want to know the absolute minimum number of tests I can run to get a reliable profile of my checkpoint. So how did the researchers use BENCHPRESS to identify the most predictive subset of probes?
They simulated a budgeted scorecard recovery using a greedy search algorithm. So to find the optimal subset, the algorithm has to maximize the mutual information between the observed subset and the unobserved remainder of the matrix.
Okay, so it iteratively selects the benchmark that most aggressively reduces the uncertainty of the entire matrix.
Precisely. And they found that to predict the remaining 133 benchmarks, the magic 5 probes you need to run are GPQA Diamond, HLE, which stands for Humanities Last Exam Code Forces, MMLU Pro, and RSA AGI1.
Just those 5 probes. And what's the error rate if you only run those?
Running just those 5 yields a median absolute error of 3.93 points across the entire rest of the matrix.
That is wild. But let's look at the compute cost of that specific subset for a second.
It's high.
Yeah, HLE and code forces require serious execution environments. They are notoriously expensive and time-consuming to run securely. If you are doing continuous integration testing on, like, nightly model builds, running code forces every single time is going to completely blow up your compute budget.
The researchers actually anticipated those exact practical constraints of ML engineering pipelines. So they restricted the greedy search to a low-cost allow list to find a budget-friendly alternative.
Okay, what's the cheap set?
The resulting cheap set is GPQA Diamond, MMLU Pro, Aider Polyglot, Math 500, and AIM 2026. Evaluating these 5 still locks down the rest of the board to within 4.55 points of error, but at a fraction of the inference cost.
Here's where it gets really interesting. When you look at the composition of those 2 lists, almost all of these highly predictive probes are heavy reasoning, complex math, or advanced science benchmarks.
Yep.
I mean, GPQA is graduate-level physics and chemistry. AE is elite competition math.
Mm-hmm.
Why do these specific disciplines hold the keys to the entire latent manifold? Why isn't, a creative writing or a basic instruction following benchmark in the top 5?
Well, it comes back to information theory and the properties of the rank 2 geometry. You want probes that maximize entropy and provide the highest discriminative power across the model distribution.
Right. You need signal, not noise.
Exactly. Creative writing or basic conversational benchmarks have massive score compression. Almost all frontier models do them pretty well, so the variance is low. Math and multi-step reasoning, on the other hand, provide a high-entropy, unambiguous signal.
Because it's purely objective.
Right. If you know exactly how a model navigates formal mathematical logic on AME, you essentially know its total underlying compute budget and representation power. That strong, clean signal allows the ALS algorithm to cleanly triangulate how the model will perform on easier, noisier, or just less structured tasks.
Math is the ultimate high-variance stress test.
It really is.
But let's talk about how this translates to deployment decisions. If I'm an engineer selecting a model for a production environment, I care about relative performance, right? I need to know if Model A is definitively better than Model B for my specific use case.
Sure.
So if BenchPress has a 4-point error margin, does it scramble the leaderboard? Or does it preserve the competitive rankings?
That is a critical constraint for any evaluation proxy, and the researchers tested exactly this. Allowing a 5-point margin on the true scores, BenchPress preserves 92.1% of all pairwise model rankings on the same benchmark.
Oh, wow. So the latent structure is that stable.
Very stable. If Model A is genuinely better than Model B by a meaningful margin, BenchPress's predicted scores will almost always reflect that correct relative ordering. You won't accidentally deploy the weaker model just because of an imputation artifact.
Okay, predicting scores for models that existed concurrently when the matrix was built is impressive, but I mean, the AI landscape is incredibly dynamic. We are constantly seeing new architectures, new post-training reasoning pipelines.
Yeah.
Can BenchPress generalize to a model from a completely new generation that hasn't even been released yet?
To prove its out-of-distribution robustness, they designed a temporal stress test. They artificially rolled back the clock on their dataset.
How far back?
Well, they trained the BenchPress predictor using exclusively older models, completely withholding any of the newer post-DeepSeek R1 reasoning models.
Okay, so the algorithm had zero exposure to the shifting frontier of reasoning models during its training phase. It only knew the geometry of the older generation.
Exactly. And then they asked the algorithm to predict the scorecards of those new reasoning-heavy models.
But did it hold up?
Even under that strict temporal holdout, the results were incredibly robust. When they fed the algorithm just 5 seed scores from a brand new reasoning model, the predictions for the rest of its 133 benchmarks came within 4.83 points of the true values.
That's practically the same error rate as the concurrent models.
Yeah. And if you give it 10 seed scores, the error drops to 2.57 points. This proves that the structural relationships between benchmarks, the actual shape of the capability manifold, remains remarkably stable over time, even as the models themselves push the absolute frontier forward.
The relative difficulty of the benchmarks scales consistently.
Exactly.
That temporal stability is fascinating. But as engineers, we know that no statistical imputation tool is infallible, right? You cannot blindly trust an algorithmic prediction without a confidence interval.
Never.
We need a rigorous way to detect out-of-distribution inputs or high epistemic uncertainty. How do we flag our own homework and know exactly when BenchPress is just hallucinating a bad score?
So the researchers conducted an exhaustive hypothesis analysis on both the benchmark side and the model side to isolate the exact variables that cause the predictions to break down.
Let's start with the benchmark side.
On the benchmark side, rejecting hypothesis 3 proved that it is significantly harder to predict a benchmark if it exhibits a wildly wide score spread across models. If performance on a specific task is inherently high variance, chaotic, or overly sensitive to prompt formatting, the ALS algorithm struggles to anchor it in the latent space.
That makes sense.
Conversely, a benchmark is very easy to predict if it has high target coverage, meaning a high density of models have already been evaluated on it, and if it has highly correlated neighbor benchmarks in the matrix.
Okay, so if a researcher introduces a completely novel benchmark, testing a capability fundamentally alien to anything we've measured before, BenchPress will just naturally flag high uncertainty.
Yes.
Symmetrically, they tested hypotheses on the model side to see what makes a specific LLM easy or hard to predict. And the results regarding model capabilities were actually highly counterintuitive to me.
How so?
Well, you would naturally assume that a massive, highly complex reasoning model with intricate chain-of-thought protocols would be much harder to predict than a simple, small base model.
Right. Sure, you would think that.
But the data showed the exact opposite. Reasoning models are actually easier to predict than non-reasoning ones. And high-scoring frontier models are significantly easier to predict than low-scoring, weaker models.
But if we look at the signal-to-noise ratio, it actually makes perfect sense.
Just there's less noise.
Exactly. A highly capable reasoning model produces very consistent, deterministic logic. It either successfully executes the multi-step math or it doesn't.
Right.
A weaker, low-scoring model relies heavily on memorized heuristics, flawed pattern matching, or just lucky guessing. That injects a massive amount of random statistical noise into its scorecard.
Oh, and that noise disrupts the smooth geometric gradients that the ALS algorithm relies on, making the matrix completion much harder.
Precisely. They also confirmed that you need recent models in the training matrix to serve as reliable structural anchors for new releases.
So to operationalize all of these insights into a usable engineering tool, they built the hybrid reliability estimator.
Right.
Rather than a simple weather app analogy, this functions much closer to out-of-distribution detection or epistemic uncertainty measurement in Bayesian neural networks. It is a layer sitting on top of BENCHPRESS that flags the confidence of its own predictions using two main signals.
Right. The first being ensemble spread.
Yeah, how does that work?
The ensemble spread measures the variance across different algorithmic initializations and variants. So if ALS, k-nearest neighbors, and SVD all converge on wildly different predictions for a specific cell, the ensemble spread is high.
Which indicates deep structural uncertainty.
Exactly. The second signal is matrix support, which quantifies the actual data density backing that specific prediction, basically looking at how many observed scores the model has in the matrix and how tightly correlated its nearest peer models are.
So it's a confidence interval. The hybrid reliability estimator tells the ML engineer exactly when a predicted score is deeply anchored in the latent geometry and statistically safe to trust, and when the prediction suffers from high epistemic uncertainty.
Right, meaning they actually need to spend the compute budget to run the evaluation harness themselves for that specific metric.
It transforms BENCHPRESS from a theoretical observation into a robust, deployable systems engineering tool.
Yeah, if we synthesize the broader implications for the field here, we now have a rigorous mathematical proof that running 100+ distinct benchmarks for every single model release or checkpoint is largely a redundant exercise in compute allocation.
It fundamentally rewires the economics of model evaluation. Using BENCHPRESS, you can run 5 carefully selected high-entropy math and reasoning probes and confidently impute the rest of your comprehensive scorecard with a known, quantifiable confidence interval.
And this allows engineering teams to reallocate thousands of dollars and days of GPU time away from redundant evaluation pipelines and push that compute back toward actual pre-training, hyperparameter optimization, or exploring genuinely novel capabilities.
It streamlines the entire development lifecycle, allowing researchers to iterate much faster based on a tiny fraction of the standard evaluation cost. But this incredible efficiency also leaves us with a highly provocative and somewhat unsettling realization about the nature of our current architectures.
Yeah.
If 133 supposedly diverse benchmarks, testing everything from raw Python coding to complex cellular biology to multi-step agentic behavior to nuanced creative writing, if all of that mathematically collapses into a flat, rank 2 capability manifold, does this mean current LLMs are fundamentally monolithic in how they scale? Are we just building the exact same cognitive engine over and over again, just in slightly different sizes?
Yeah.
Or worse, are we just failing as an industry to invent evaluations that actually test genuinely diverse orthogonal forms of artificial intelligence?